Hello, everybody. Okay, can everybody see me? Can you all see me?
Yeah.
Okay,
Yes,
well,
sir.
okay. We're waiting a minute or two because we've got only 8 people in here, so I want to make sure everybody gets here. Has anybody here heard that more people are being sent home, or? They're all, oh, okay, that's cool. All right, let's see. Well, there's 12 there, so we have more than 20 people in the class, so that's why I wanted to wait a minute. Those of you online, do you have any questions before I start?
Is the exam still next Monday?
Yes, that's the plan. I'll see how it goes tomorrow, but that's the plan. Basically, I'm going to go up through Lewis dot structures and stop the orbital shapes and everything, the VSEPR model and the other things that come a little later. That'll be covered on the next exam, but this one we'll just stop with Lewis dot structures and hybrid orbitals, and that kind of finishes it for what I'm doing. And I'll finish that tomorrow. What I'm doing today is going over covalent bonding and starting Lewis dot structures today. So are there any other questions anyone has? Anyone local have any questions? Okay, now, all right, let's get going with this and take up where I left off. Now, it's chapter 6 in our book, as well as the Chang chapter 9, but again, the slides are better. The slides are better for these slides than the other. What's weird about chemistry textbooks is they have different authors for the chemistry textbook, and so it's the kind of thing where, in a way, those of us who've have used a lot of resources, we try to use whatever resources we can to make the best thing for the students. So please keep that in mind too. And what I want to do also is reinforce the fact too that I would like you to please continue to read the book, the chapter. Like, for example, now I'm in chapter 7. So you read the chapter, you see what the things that are covered in the chapter. You're responsible for everything in the chapter. You read it and you do the little problems within it. There's a worked out problem for you and a little practice problem within the text. So basically you need to do those all along. And then at the end, you pick 2 or 3 questions from each section behind at the end of the chapter and check your answers in the back of the book. I believe the odd or even ones have the answers in the back. And then if you get one wrong, go back and look at the text and try and fix it. And then at the end of the chapter, you could take the practice test. But unfortunately, we have some people, and I've had this wherever I've been, whether it be Nazarbayev University or at the American University in Iraq, people trying to study from the PowerPoints. What is the purpose of the PowerPoints?
Wait, so Dr. Douglas, are we on chapter 6 or 7?
What, we're on 7 now. Okay, what is the purpose of a PowerPoints? To give an overview and also to spare you bad handwriting all over the board. Because what we used to use before PowerPoints when I started in the early 90s was I would just write on the board everything that's on the PowerPoints. And it makes it a lot easier for a professor to use that as a resource. But unfortunately what it does is it leads to worse instruction because a lot of professors get lazy and just throw up the PowerPoints and then read them and then kind of talk about them and then they go away and then they expect you to do your work. Well, I'm not that type of thing. I try and do it, both of them together. And so I appreciate you putting up with my handwriting, but the purpose of my handwriting is so you can follow my train of thought and expand it. And then you can do the reading later and see, oh, that's what Dr. Douglas was meaning, because you can see it in context. So you get the verbal aspect of my lecture, you get the writing down of the notes, and you get the other aspect of the PowerPoints refreshing your memory, as well as the practice problems you work on. Now, the lattice energy, again, I was talking about lattice energy last time, and what I'm going to do now is continue with where we left off, talking about this essentially. You have the charge difference with the radius there. E is the potential energy, Q is the charge on the cation, Q minus is the charge on the anion, and R is the distance. And basically, I recommend you practice a couple problems that are in the book, just plugging those numbers in. And if I'm ever asking you on a test or quiz to do that, you just put them in there and just practice a couple just so you could do that. But I really have seen pretty good work there. But also when you have the lattice energy associated with this, I talked about last time, the magnesium oxide is a higher lattice energy because there's a charge difference of 4 between it. Sorry, my chair is getting falling down on me. Okay, so basically the key thing is just to keep in mind charge difference is very important, and it's even more so important in electrochemistry that's covered in Gen Chem 2. And then these there. So basically the lattice increases as the Q increases or the R decreases. And then there's an example Born-Haber cycle, and your book talks about that. You don't know what delta H's are yet because that's covered in chapter 9, I believe. Yes. Sorry? This? And it's in the slides, and it's also in the video from before too, so you could refer back to that later. Did you
Dr. Douglas?
Yes.
How do you find the R?
Well, basically that's done experimentally with the crystal structure.
But will it be given in the problem that you ask us on the test?
Well, yeah, if there's a problem on the test or quiz, I'll give you R, yeah.
What about K?
You don't have to memorize that. It's just a matter of plugging the numbers in. The same I give you K. Okay? And I just want you to get the big picture. Now, lattice energy, this shows the different examples there, and then sodium chloride and how that works. Now, basically here, the first kind of bond, and I'm just going to start drawing on this now, just so you can see how this works. The first kind of bond is when you have like sodium that is a thing like this and a chlorine that has 7 around it. And I'd really recommend you practice by putting those things in there. This is an ionic bond, and essentially you get the exchange of electrons. And then it results with sodium plus and chloride minus. And practice even the naming by saying sodium plus and chloride minus then when you do that, okay? But basically this is an ionic bond. Now what I'm going to do now is erase this, and we're going to talk about the next kind, which is called a covalent bond. And this is where, for example, with 2 hydrogen atoms. Oops. With 2 hydrogen atoms. If you have a hydrogen atom here and a hydrogen atom here with 1 dot for it, how can they both get 2 electrons? They both want to have 2 electrons. They're equally strong. So say you have, like my granddaughters, they're twin girls. They both want to have a toy or 2 toys. They both want to have 2 toys. How do they have both 2 toys? They share it, okay? So basically you bring these 2 together and you put the 2 little dots like that, okay? And then that is transferred to a little line. And this indicates what is called a covalent bond. And there's no charge associated with it because they both have their original electron around them. They haven't shifted to 1. They're pretending, why is this pretending to be helium? Pretend helium. Why is it pretending helium now?
Because the hydrogen, they both have 2 electrons.
Yeah, they both have 2 electrons, okay? They just happen to be rotating around different places, but they both are happy with 2 electrons, okay? So that is the nature of a covalent bond. Now I'll get rid of my bad handwriting, okay? Now, why should 2 atoms share electrons? Well, they want to fill up the orbitals and pretend to be neon or whatever else. So if you've got fluorine there that has 7, and it reacts with another fluorine that has 7, how can they both have 8?
They can both share just one.
Yes, they share the one in the middle. So you get like this, F and then a line and then another one, or you could use 2 dots if you want. I've had students continue to use the 2 dots at this stage as long as you want, but I just encourage those who are ready can switch to just do a line, because a double bond is with 2 of them. Okay? So let's look at one with 2 of them. CO2. Now, this is where you use your periodic table. Remember the periodic table I asked you to print out and whatever else, where you have the X above it, and then the X there, and then the 3 of them around, et cetera, going like that. So basically what we're going to do is put the pieces together here. If you look at the carbon, it is 4 around it, and it's got 2 oxygens. And so let's be logical about this. Where's the best place to put the oxygens? So they're all around the carbon. On either side, very good. So you put one over here with 6 and one over here with 6, and point them in the right direction when you set it up. Okay? Now, what do you notice that's really close to each of these? What do you notice? Well, this is right here. This forms a bond. So does this one. But now they're extra electrons. What will that do? You've got one here and one here. You've got one here and one here. What are they going to do? Well, they're going to share a bond also. So these go away and shift, and these will share things, and they'll get 2 of them. So now you have carbon dioxide, which has a double bond on both sides.
Dr. Douglas,
Yeah.
So carbon has 4 electrons and oxygen has 6?
Yes. Because oxygen, if you look on the periodic table, looks like this when you spread it out. Okay?
Okay, would you...
Carbon looks like this. So it's a matter of putting the pieces together and put the one with the most holes or the most places to attach things in the middle. Yes. Sorry? Well, because you've got an extra electron and they want to bond, they want to share. Well, we can set it up again. You got 4 around here like this, right? And you got an oxygen over here with a thing there and one there. And then you got another oxygen over here. There, okay? You see this pair right here? See this pair right there? That'll form a bond. This pair right here will form a bond, okay? Then this one and this one will form a bond. This one and this one will form a bond. See this one together, so you get a double bond there. It looks like this. That's a double bond, okay? And then this one and this one will form a bond, and it goes like that because it's all 3-dimensional. So you got this other one here, okay? So it's a matter of putting the pieces together. Do it a step at a time.
Wait, what other... So there's only 2 covalent bonds forming, correct?
Well, the reality, there are 4, because so I'm going to delete everything that's on the slide and show you just based on this here. When you have the fluorine, it looks like this, right? How many electrons are around each fluorine? There are 8, because this is a pair of electrons. You have 2, 4, 6, 8, 2, 4, 6, 8. So it obeys the octet rule, 8 electrons around each one, okay? They're both pretending to be neon, okay? Now with carbon, you have 4. You have oxygen that has 6, okay? You have oxygen over here that has 6, okay? How can they all have 8? Yeah, because it's a 3-dimensional structure and they rotate. And they form what are called hybrid orbitals, which we'll talk about later in the chapter. But basically you form the bond here first, and then you form the second bond with that. So now you have 4. So basically some students like to do this, have 4 dots here, to see it, and then 4 dots over here, and then the oxygen over like that. But I like to put in the 2 lines directly, and then you make the 2 lines with that, and then make the other line with that, and then you get CO2 that looks like this. That to me is more logical in the way I look at it. But if you want to use just 4 dots to indicate the double bond, you can do that.
Dr. Douglas,
Yeah.
I'm not understanding. I understand like with the connecting the two, the left and the right of the carbon to the left and the right of the oxygen, but where are you connecting the other two from? Like the other two,
Well,
the
because
bottom and top.
there's an extra electron on the top. Let me erase part of it. Now follow my logic, Nick, here. You have 4 around the carbon, right?
Yes, sir.
Okay, you have 6 around here.
Mm-hmm.
So let's go one step at a time with this. Then you pair this up, right?
Mm-hmm.
Then you pair up this one, correct?
Yes, sir.
So you form 1 bond, and that's a particular kind of bond. Then you have another one. You have one here, A, and this is A. So what are those 2 going to do? Those will share 2. So you get a double bond with this and this, okay? So now if I erase what's on the slide, I'm going to erase the slide, erase here so you can see. This has now been replaced with a double bond. Now, on the other side, you have just a single bond. You have a single bond. You have an electron here and one here. What's going to happen with those 2? Might as well ask you, Nick, what's going to happen with those 2?
Are you asking me or Nicholas? Like I was asking.
Oh, Brandon. Sorry, Brandon.
Yeah. They're gonna bond.
What?
They're gonna bond.
Yeah, they're going to bond too. Okay. You have similar voices, you and Nicholas, so that's fine. That's fine. But basically,
that's fine. But how would oxygen not get 10 valence electrons then?
Well, because it won't fit in the orbitals. It likes to pretend to be neon, not something else. There's only 2s2, 2p6, right? You can't get 10 in there. Yes.
Because I get that the oxygen then becomes neon or acts as neon, and the carbon, does that act as neon?
Yeah, because it also has 8 around it too, right? So they're all happy. That's why carbon dioxide, believe it or not, is a very stable molecule. It doesn't like to break up very easily.
Okay, so whichever word they're in will act as the
Yeah, or it could even be titanium, tin 4 dioxide has a similar structure, but that's more metallic. So there's the metallic ones have a more charge associated with it. So it's called a polar covalent bond, and we'll talk about polarity later. But right now, I'm just teaching you how to do the Lewis dot structures. It's more basic. Just start with that now. So let's use the pretty pictures on the PowerPoint now. I showed you my little style. So now you have these 2, and that looks like a jumble. But basically, this slide likes to put the double dots in there. But I just put it with a line, and you have 7 in both, and now you have 8 around both of them. They obey the octet rule. Okay, now what if you're going to do fluorine? Sorry, what if you're going to do this? Fluorine chloride, FCl. What would be the nature of that bond? Wouldn't it be the same thing? Yes, it'd be the same thing because here you have 8, you'll have 8, 7 around the fluorine. And you'll have 7 around the chlorine too. And you form a bond there. So it'll look the same as that. Doesn't really matter. Chlorine is the same way. Cl2, Br2, and everything else. And that explains why they're diatomic elements. Same thing as hydrogen. Hydrogen is the same thing. That explains it. Now let's look at oxygen. How many does oxygen have around it? The oxygen, the gas, how many does that have around it? 6. So we put them together. And how can both of them get 8? They share. So you got the ones there and then the ones there. So it essentially goes like that. Okay? So an oxygen molecule will look like this. Okay? Now, why did I move those electrons off on the side? Well, you want those electron pair to be farther away from the other ones, so they're not going to be right next to each other. They're going to kind of spread out a little bit. So basically, there'll be like an orbital that goes out like that, an orbital that goes like that, another one like that, another one like that, and so it's a relatively stable system. Okay, any questions, those of you who are virtual?
I have one.
Yes.
Is there like a certain way that we need to draw it in order to get credit on the exam? Like, are you looking for a certain drawing type, I guess?
Dots or the arrows, it doesn't matter. And that's what I'm going to sign for you over the weekend is that exercise 11.3 I sent out to everybody. So I'd like you to work on it because it's full of exercises for Lewis dot structures.
Dr. Douglas, what 11.3?
It's experiment 11.3. It's a dry lab where you essentially make models. And basically, I'm going to assign you the Lewis dot structures for the weekend of those because it's like half the exercise. But we're doing another modeling thing in lab that's virtual that'll come in at the end of the semester that involves building the structures. And basically, you can do that also with this exercise. But I want you to concentrate on the Lewis dot structures for the weekend. I might have another paper too. I have some other in my resources I can look for, but that cover that.
Was that just for your lab? Like, I haven't gotten an assignment sheet from you.
Well, the thing is, I'll send it out to everybody at the time, lecture and lab people. The lab people use it later, but the just lecture people, you'll get the assignment too. It's just, it's a dry thing that fits with a lot of dry labs fit exactly with the lecture. They're just done in the setting where if we were meeting in the classroom, I would be working with you individually on it or something like that. So that's how it works. We have all the models on the tabletop, and that's what's going to be planned for 3 weeks for the laboratory for all of you who have me or Dr. Gerhardt for the lab. Okay, now these things around it, these are called lone pairs, and they have lobes associated with them. So basically you have lobes associated with each lone pair. So if you go back, you have the lone pair here, and they look like this coming off of the thing with the lone pair. They each have their orbits, they kind of flow in, and then you have the shared ones in the middle, which is a single, and then it's given a line. Now we look at the Lewis dot structure for water. Let's try.
The lone pairs are just the ones that aren't bonded to each other?
Correct. How do we do the Lewis dot structure for water? Look on the periodic table. What column is it in? Count across. You'll always have the periodic table in front of you. What column is oxygen in? 6, yes. So how many dots do you put around it? 6. So we do it. 1, 2, 3, 4, 5, 6. Now, some people like to do it this way, where you put in one here and cross it like that. Well, I don't. Okay, what I recommend you do is spread them out just to be prepared. Okay, so basically you just spread them out and do it like that. Okay, so basically you got, I'll delete that, and now you have the dots. Okay, because when you put another atom in there, it's going to want to be as far apart from it as the other one. So now we go back to the pen, and you orient the pen in such a way that you orient the hydrogens in such a way that they're right next to it, and then you draw the line in there connecting the dots. And when I was growing up, I liked playing Battleship with graph paper. Well, you connect the dots with Battleship too, so such is life. But in any case, the point is connecting the dots is, you know, little kids that learn how to connect the dots. Yes?
So both hydrogen and the oxygen.
Correct. Yes, and they're all happy. And of course, water, as we all know, is a very stable molecule under normal circumstances. Okay, and that's one reason why it doesn't like to break up into ions. Okay, so now, okay, now I'm going to erase what's on the slide and use their art here. Okay, so you have the hydrogen, looks like that. Now this is something I find annoying about the thing. They put the hydrogen with the dot up a little bit. That's okay, but I like to do it to the side, but that's all right. It's just authors deciding to do it slightly differently, but they have them move into one another like that, and then you get the bond like that, and essentially they orient the same way. So that's essentially done for there. And you got 8 electrons, and this answers your question, Paige. See the 8 electrons around the oxygen? Okay, and you got 2 around each hydrogen, so they're happy there. Okay, single covalent bonds. Now a double bond shares them. And this is CO2, what I showed you before. And the way that's represented as that. Okay, and you can do it again for yourself. You put the C, oops. You put the C like this with 4, 1, 2, 3, 4. An oxygen over here with 6. Another oxygen over here with 6. You combine them, do those automatically. Then you look and see you got this one and this one, so that can form a bond. You've also got this one and this one, so that can form a bond. The result is there. So that's sort of the intermediate step. And I recommend you practice just the same way I did on the thing. Use pieces of paper to write these out as you're going through the chapter. There's going to be a whole lot of little examples in there in the textbook. Okay, so it is really, if you keep it simple, it's really easy to learn this stuff. Okay, so now you got 8 electrons around each one with double bonds, and then double bonds look like that. Now, triple bond. Let's do it. Oops. I don't want to do that part on the slide yet. I want to have you think about it before it's given to you. Now, nitrogen is another common dual thing. How would you form that one? How many, look, what row, what column is it in on the periodic table? Number 5. So you put a nitrogen net there, and you put 5 around it. You put the pair over here, one like that, one like that, one like that. Then you put the other hydrogen, nitrogen there, put a pair there, one like that, one like that, one like that, and then you form the bond. One bond there. What happens to these 2 electrons? What happens to these 2 electrons? Anybody distant want to answer that? What happens to those 2 electrons?
They bond.
Yep, they bond, form a double bond then, and then these 2 electrons here, those will form a triple bond. So then you get the nitrogen with a triple bond in the middle with electron pair on each end. Now, just to introduce the topic, this one and this one have something in common. What is their shape? Just be logical here. What are they shape? If you were to draw it, what would be their shape? Would it be a triangle or a line or square? A line, so they're called linear. So that's the first shape you're going to learn, is linear. Okay?
And that's triple bonds?
Yeah, with triple bonds, they're linear bonds, yes. Yes, And you'll learn why when we talk about how the electrons do this. Well, not really, because I'll give you an example of that. Okay? What? No, what I'll show you, give you the periodic table and put like CO2 on it, or let's do this one, CH2O. Yeah, then I want you to do it. Okay, so let's do it. That sound good? Okay, you put the carbon where? In the middle, because it has 4. 1, 2, 3, 4. Okay, that you then put the oxygen next to it, right? So you put an oxygen over here and be logical about it. Okay, you can form a bond there. Now, you have how many odd electrons do you have that haven't been paired? How many holes do you have that can form bonds there? No, there's 4. 1, 2, 3, 4. There's 4 lone electrons, right? But you only have 2 hydrogens. So where's a good place so you can get this? Well, you take one of these and you form a bond with this and you form a double bond. There. Now you have 2 electrons available, and this will form a hydrogen there, and that'll form a hydrogen there. So the resulting structure looks like this. No, this is a different example. What does that look like? A triangle. So that's called trigonal planar. It would be flat. So it's not linear because these hydrogens are sticking out on the side. Yes, and basically I appreciate you folks thinking ahead here, because essentially we're going beyond the thing as to where logically this continues. So that's, you're thinking like a chemist. Okay, yes.
Can you?
Well, a common mistake people make is this. They put the oxygen there and then a hydrogen there, and then you've got an extra one there, and there, and then you got 3 around that. Can you put 2 hydrogens in it and use up the extra? No, you can't. Because if you put 1 over here, what's going to happen? You have 3 odd electrons that haven't bonded with anything. Okay, so you got to do that later. You got to do that later with filling up the holes, like you're connecting the dots again in an appropriate way. But this is a very common error to just line it up. Yes, I'll be doing plenty of them. Okay, so let's go back to, let's erase what's on the slide. But remember, this is all in the recording. You can see it again with my bad handwriting next to it. So now you got a triple bond here. Going to the next one. Okay, so the triple bond looks like this. There with the triple bond, 8 electrons around each one, and then you got that with the triple bond there, and then it goes into lengths. Now, why is H2? Why is that radius smaller than HI? Yeah, there's 1 electron and they're both smaller. Both hydrogen atoms are smaller. The iodine is very big. So it'll push the hydrogen atom further away from it. Okay, and so basically, if you have a triple bond like N, the triple bond will be the shortest, and be logical about it too. Why is N, triple bond N, going to be shorter than oxygen, double bond oxygen? Why is that shorter? They're both pretending to be neon, but why is that shorter? The triple bond holds it all together, like using 3 rubber bands around something, okay, versus 2. The 3 rubber bands is tighter, and so it'll want to be one more cohesive unit. So triple bonds are always shorter than double bonds. Okay, that's called average bond length. Now, appearances of general things. When you have ionic bonds, they're usually salts or other kinds of things like that. They have very high melting points, etc. But there are a lot of things with covalent bonds that are either liquid or even a gas. So that's very aspect of this. Now,
I'm sorry, Dr. Douglas, you said the nitrogen bond was shorter because it's more like tightly compacted?
Yes, correct. And you can see this on this chart. Like here, the carbon triple bond is 120, the carbon double bond is 133. You've got it, the CN bond there is 116. It's a triple bond, but they're not showing nitrogen. I just said that and said basically, I don't have the number handy. I don't memorize the numbers. But the thing is, that's even shorter than the other one. Okay. Because even this one has an electron pair over here and has a -1 charge when it's in that form. Okay, so now the comparison between the things, and basically when you talk about ionic solids versus covalent solids, they have different things, and that's described later. Now, polar covalent bond is one of the next steps. What I want to do is go for this one. Before I talk about this is here, the whole concept of electronegativity. Electronegativity is the ability of an atom to attract towards itself the electrons in a chemical bond. Okay, that's a very important concept. And if you were to look on a periodic table like this, here, you got a periodic table looks like this. And just remember what we learned before. Which ones are more likely to drag electrons to itself? Which side like to be minus something? The ones to the right. So electronegativity will go up on this side. So you got fluorine over here is very electronegative, okay? It likes to draw electrons to itself, electronegative.
So what about going up and down on the periodic table? Is the decrease or increase going up or down?
It'll decrease. Why do you suppose that is? This is not electronegative. It'll give them up, not electronegative. These are the more positive numbers, like cesium likes to give away that extra electron because it's bigger and forms cesium +1. So essentially the trend is it's more electronegative as you go to the right on the periodic table and less as you go down because the atom gets bigger, because there's a more barrier between the electrons and the nucleus. That's related to effective nuclear charge that we talked about before. So basically, if you've got like HF, and this explains why HF, when you dissolve it in water, is a weak base. These electron pairs, this is very electronegative compared to the hydrogen. So where is this electron pair going to be closer to the other one? Well, it's going to be more around the fluorine. This will be the fluorine. This will be the hydrogen. So essentially, the electronegativity aspect to this, and this whole thing of being more negative on this side and more positive, this is called polarity. Okay, and now I'll go back to the previous slide. And this essentially is electron poor, electron rich. And so basically, this is called a polar bond or polar covalent bond. And the whole concept is called polarity. And essentially, you've got an arrow. You have a plus on this side, and then an arrow looks like this. And this is considered a vector, if you know what vectors are from math. But basically, this is the arrow, and it points in the more electronegative direction. Okay, so basically, as you go across the periodic table, and I believe your book has a thing with trends going across the periodic table, the more electronegative goes over to the right, and then goes down as you go down, like I showed on the next slide with this, with electronegativity on this slide. Now, I'm going to erase what's on the slide now and go back. The next part is electron affinity.
Dr. Douglas, I'm sorry. So the polarity is higher when it's more electron rich?
Right.
Is that like all there is to do with it?
Yeah, because the fluorine end is more negative than the hydrogen end.
Okay.
So like, for example, a polar solvent is water, because you got the oxygen like this, and just look at it logically. Which sides are going to be negative? Which parts are going to be negative there? Whoever asked me the question, was that you, Brandon? Which parts are going to be negative?
The hydrogen?
No. Which parts has the electron pairs that are sticking out there?
I'm sorry, what do you mean?
On this water molecule, where are the hydrogen pairs? Pardon my art. My art got messed up on this.
The pairs are between the hydrogen and the oxygen.
No. The lone pairs, where are they?
Where you just erased them.
Yeah. So
Those
the lone pairs will look like this. So what is going to be the negative region?
The negative region?
Yeah.
Of the polarity?
Yes, the negative region. These are 2 electrons, correct? You see the 2 electrons? And that's your question too. So those are going to be negative. This will be negative. This will be negative. The hydrogen will be more positive. So this is considered what's called a polar molecule. Okay, it's a polar solvent. And that's why water dissolves salt very easily. Okay, so this polarity of the bonding is very important. Now, electronegativity, electron affinity is related to that, and it's measurable. When it's measurable, chlorine is the highest, and then essentially it grabs the electron to itself, and electronegativity, fluorine is the highest, okay? Because it is the smallest atom on the top that wants desperately to have 8 electrons around it. So it'll grab them from anywhere. And that's why fluorine gas and hydrogen fluoride are very, very reactive materials and can be very dangerous if they react with other substances, because that fluorine is a very, very reactive atom. And that's part of why, particularly when it's not in the fluoride form. Now, electronegativity of common elements, and these are with the numbers. As you go down the periodic table, it's less, and as you go across, it is more. And this is logical because over here, everything likes to be -1, -2, -3, okay? Over here, they all like to be +1 or 2 or +3, okay? So essentially, the more electronegative, the more it's going to want to drag electrons to itself. And that's a chart. You can use that when you set up something to get differences. Like say, for example, you're going to do a water molecule like this. You can look at the differences between them. The hydrogen is 2.1 and the oxygen is 3.5. What's the difference in those numbers? 1.4. There's a 1.4 difference. So the arrow will be directed towards this end. This is the vector. And here, this arrow will be directed towards there too. And it'll be like that. But if you got 2 chlorines next to each other, what is the difference between the 2 chlorine numbers? You just have 2 chlorines. They're both 3. So what's the difference there? 0. So if you have a 0 difference, it is called just covalent. Okay? If it is anywhere between, it would be called polar covalent. And then if you've got like cesium fluoride, which would be like this, cesium is 0.7 and fluorine is 4.0. The difference there is 3.3. So 3.3 difference. So there'd be anything above that, that is considered ionic. So basically it explains why some are ionic and they want to break down and easily dissolve in water, because the more ionic they are, the better they'll react with water and dissolve. No. It'll be provided for you, whatever else. And that's where you work on the problems. And that's the homework problems for this is most important, because then you get the trend. If you just remember the trend, you can say what's more polar and whatever. If you're shown a molecule, say what's more polar than the other one, and just remember it. Okay. Well, electronegativity. Well, that's the tendency to want, it wants electrons. It's measurable. Whereas electron negativity is more subjective. And the variation of electronegativity, they've got a little chart here for that. So basically classifications of them between it, if you got a difference of 0, the bond type is covalent. An example of that would be chlorine. Okay, the difference there is covalent, okay? If you got above 2, and that would be like cesium fluoride, where you have a minus here, a minus there, and a +1, that difference is 3.3. That's considered ionic. So essentially you go there, that's considered ionic. Anywhere in the middle between both of them, that would be polar. And so an example of that would be HCl. HCl, and which side is more negative? The chlorine. This is the negative end. This is this. And you can put the numbers in. This is 2.1 and this is 3.5. So the difference there is 1.4, but that is considered polar covalent. Okay, so that's polar covalent in between. And essentially an increasing difference in electronegativity, covalent shares, polar covalent partial transfer of electrons, and then ionic transfer of electrons at the end. And then the next slide, it gives you a little quiz, but basically we'll do that next time. I think we've reached the time for end. But this is enough for you to work on tonight. And so in the book, please work on the Lewis dot structures and the ionic structures, the homework problems in that. If you want, and again, as I told another student yesterday and last week, the purpose of Hein, the PDF I sent you, which is an intro to chemistry book, is just if you need background material and I want more simple problems related to my whole way of thinking, feel free to review that first, but you do work the problems in our textbook, okay? Any questions? Okay, very good. Any of you distant, any questions? Okay, we'll probably finish what we're going to do for the exam tomorrow. Have a good day, everybody.